Excellent. Is that a peppermint patty yellow?
Yeah.
Nice.
That's awesome.
Those are pretty awesome. Okay, let's just take a minute to come into the room, come into this space. Got a different one for you. And now I have to shake it up because I got folks who are here for 2 classes in a row. So we gotta like get a little spice in all of this. So let's get spicy. Let's just take a minute. Stop doing what you're doing. You do not have to participate, but I ask that you not do other things that make noise or move or breathe or any of that stuff. Just stay still. We'll just settle into our bodies. And what that means is just relax. Your eyes are closed, but you can still see. It's dark. Notice that you can gaze into that space. Maybe like looking into a dark room, or a room with a very faint light. Without moving your eyes, keeping them very soft and relaxed, can you notice the edge of your visual field? What shape is that space, if any? You might be seeing shimmering or patterns forming. You might not see any of that. Some people don't. Just relax and let that space be the thing your awareness is aware of at the moment. We're all scientists of some sort. You're a math scientist or an actual scientist, a physical scientist. What do you notice about this experience? Took a little voyage to a nice, peaceful place. So before I begin anything, I've got a hint on one of the homework problems I would like to give, because you might not know where to start on the current homework. Homework 2, this will be due start of class next Wednesday. That's probably way more time than you need, but that's what it's going to be. And do you have any questions over homework 1? Anything you'd like to talk about besides polar coordinate stuff? Because I'm going to talk about that today, so I know that's a question, possibly. Cool. There's one problem where you're asked to show, I believe, is that true? Cool. Pretty straightforward. The tip is to, and if you're not used to writing math, I'd like to ask you to use more words than maybe you're used to. So if your last math class or your only math class has been calculus based, I'm going to ask you to just practice writing things a little more, just a few phrases. And the easiest, the best math phrase, the most primal one is let. So we get something to handle while working through this. So I would just start, everybody's problem should probably start like this, and it should have the word let, because otherwise there's just weird shit floating around on your page, right? So now I know, this is what they're assuming. Then, what does that represent? Conjugate, exactly. So the conjugate, if this is z, x plus iy, here's my real axis, here's my imaginary axis, and I draw a little line like this, and we're gonna actually move right into this. That z, Christian, what is z conjugate, do you remember? This guy, what would z conjugate
be
look?
x minus iy.
Yeah, so thank you. It basically says take your z and flip it over the horizontal axis. So there's this lovely geometric relationship between z and z conjugate. Proceed from there. There's actually very little to do after this, but I just wanted you to be aware of the conjugate, and in particular, this relationship will come in handy just numerous times throughout the semester. So good to know. And I wanted you to also know about this geometric aspect of it. So there's no questions on the non-polar stuff at this point? We feel, okay, cool. Let's get rolling. Let us roll. So I got a great picture up on the board. I'm gonna come back to it. I've got this complex number, z. It's x plus iy. That is essentially identifying it in the plane as, bless you, as x comma y, the point xy. Remember, this is my real part. This is my imaginary part. So this is a two-dimensional space. It's the plane. It's this board extended forever. It's this idealized piece of paper on which we do all our time. Keep teetering over here. It's a two-dimensional thing. One way to think about dimension is how many pieces of data do I need to describe a location? That's a good way to think about dimension. So in the plane, we need two pieces of information, x and y. On a line, on just the number line, you just need one place. You probably need to know where 0 is so that it makes sense to talk about being somewhere. As soon as you set 1 point, you know everything about it. As soon as you set 2 points, you know the scale. But that's a one-dimensional thing, because I only need one thing to know where I am in that world. So this is 2, but it's not the only way to describe every point in the plane. So another way to do this, and this is the way you learn from grade school up. This means how much left and right do I need? Positive x's to the right, negative x's to the left, and this is up and down. So it's telling you how much to move left and right, how much to move backwards and forwards. Another way to describe that exact same location is as follows. First, let's see. So if I wanted to describe how to get from myself to Cecil, right here. One way I could do it is say 1, 2 steps forward, rotate 90, 1, 2, 3, and it looks like 4 would put me right there. So relative to here, I could say Cecil's coordinates are 2, 4 relative to my current location. Another way to get to Cecil would be this. Rotate 60 degrees, and then walk forward that distance, whatever that's going to be. We could figure it out with the Pythagorean theorem and stuff like that. But that gets me to the same place with a totally different mode of description. So that's what we're going to talk about today, which is the polar form of complex numbers. How many folks have done polar coordinate stuff at some point in their lives? Okay, I'll get it. Cool. So if you've seen this before, it's basically very much the same stuff you've learned before with a big caveat and a deep, beautiful twist onto it. So polar form, let's think about how I describe that. Sweep out an angle theta. And this is essentially, we're going to call this 0 radians. This is home base. So the positive x-axis is our standard position. Everything will be measured from there. If I sweep counterclockwise, this is positive angle. If I sweep clockwise, that's negative angle. So I sweep out the direction and I make sure that I have the thing in my sights. And then I describe how far from the origin do I walk forward in that direction to get there. So from here, I'm going to walk whatever required distance I have to get to that. And that distance is just that length of that line segment right there. So now I can describe every point Z in another way. I can describe this in polar coordinates. And this, I'm going back to the stuff that everybody who raised their hand, this is what you used to think of it in terms of. In r comma theta, you would tell the sweep and the distance to walk. We're going to make that a lot more sophisticated and a lot more beautiful now. Up on our webpage, I put a little exposition of a quite beautiful fact. So you might want to watch this if you, sometimes you don't get to see this in Calc 2, but please watch, and just to refresh your memory, the derivation of Euler's identity. That's in the content area. There's actually a bunch of different ways to get this identity, but the series method that I have up there, that's my favorite. It's the one that just, it's really cool, just very magical. We're gonna get to that today. But let's see if we can just make a couple switches back and forth here first. Let's just do a little bit before we get to that with what we have here. How could I compute, if I knew this, so given this, how could I compute this r and this theta? Can somebody help me out here? How could I find r? How would you find it? This is right angle here, here's r. What's this? That's x. That's y. How do we find r? Pythagorean theorem. We're freaking summon Pythagoras right now. I'm actually working on this art project of these little summoning circles for different mathematicians. Yeah, and I'm working on Pythagoras right now. It's going to be pretty awesome. Pythagoras was way weirder than I imagined. So I've been spending my spare time researching things I didn't know about Pythagoras. He didn't even invent that Pythagorean theorem. That was known to the Babylonians. I just found out like 2 days ago. But Pythagoras got the credit. So I could use the Pythagorean theorem. Christian, that's right. Could you please, what would I write next here?
Well, I guess like all out it'd be like the square root of x squared plus iy squared.
Ah, cool. So I love that you put that in there, but let's keep in mind that this y here is actually just a real distance, so we'll keep the I out. So it's just y squared. Yeah. What is that in terms of complex numbers? So we learned a bunch of things. We know that if I have z, the conjugate I can find. What's that? That's the modulus, and that's the modulus. R is literally just the modulus of the complex number. So take a note here that r is the modulus of the number. It's distance from 0. It's absolute value in a way. Ooh, okay. Help me out with theta. How could I find theta? Trig, friends, shaking the dust off our trig, and this is, I've never sat like this. This is super comfortable. Very supportive. Kitra.
You could do arctan.
Beauty. So we could say that theta is arctan of what, my friend?
Over x.
Yeah, I love it. Awesome, thank you. Cool. So to move from rectangular form to a polar form, I could use those formulas. Now let's kind of work it backwards. Now, let's say I gave you the polar form, and we're just warming up here before we get to Euler. So suppose I have a z, and here I've got modulus of z, that's that distance, and I have theta. So right now I've got this picture. We want to write z in rectangular form. Someone guide us, please. It's like literally like an auction in my class is the subtlest pinky flex.
So I mean, like, if you have a nice angle that we know, like, the sine and cosine of, right, like pi over 3, you can just pull out that identity for the, like, x and y. Otherwise, you could do the tangent of the angle, and then you could try and get the fraction out of it, and that's gonna be like your, so it's gonna be like modulus z times that identity of the x and y, and so then you're just gonna multiply it all out by modulus.
Cool, that's a beautiful but abstract description of what needs to happen. Yeah, lovely. Let's just write out a couple basic trig facts that are gonna help us just, live. We're math folk, right? We have to have some basic sustenance. In terms of this picture, so this, I'm just saying what Lou said with the deeds in there. What is cosine of theta in terms of this picture?
Y over x over
X over.
modulus.
Oh no, yeah, actually he convinced me he almost convinced me. Yeah, cosine is adjacent over hypotenuse. Ka, right? Ah. X over modulus of z. And then, and Vivian, this was the first one we went for. Sine is opposite over hypotenuse. So that's y over modulus of z. So that actually tells me how to get x and y. I just solved those equations. Provided I know this length right here, which I will, because that was the piece of data I was given. I was given this length and this. Remember, this is just r. So if we take these and solve them, we get x equals the modulus of z, r, cosine of theta. So let's write that. And y equals modulus of z sine of theta. And that's just r sine of theta. Let me stop. Let me know. Anything you want to talk about, ask about, clarify? Little basic trig review, right? Nothing, not even complex numbers yet. Now we're going to go complex. So this is the x thing here, this is the y thing. So z is equal to r cos theta plus the y component, this y height, right? It's just x and y. And that's, I'm going to put the I in front so it just kind of separates itself, r sine of theta. And this is called polar form of a complex complex number. Seem right? If you read ahead, this probably looks not alien. Recommend reading ahead when you can. Oh, speaking of which, Ella sent me, and it made me so happy to see it in my mailbox this morning, a really nice video on just the weird geometries we're gonna study. So that is up in the content area too. So thank you, Ella, for that. It's a great video. It was actually one I watched during my moments of desperation and darkness early in the break. It's a good video. It won't help you with any of this, but it'll give you an overview of the things ahead. So we can actually rewrite this. I can pull that R out. And I get this. Now, this thing here, what is the modulus? So if I just have this complex number, let's just do a little scratch over here. What is the modulus of this complex number? So let's say, I'll just write it out. I sine theta. Theta is just some real number. What is the modulus of that number? So how are you doing that, Nathan? I think I was hearing the truth.
But then you have to take this.
That's good. That's good. So Nathan is coming back to this formula that if we had this, and you can look at the picture and see that that's the case because that's just the modulus. So what do we get here? So we get square root of cosine squared plus sine squared, and anything just wickedly beautiful here?
It's 1.
Which is 1? Yeah, this guy right here, right? That's a trig identity, that's 1. Do I need to prove that? Because I can. No, okay, cool. I'm not sure if you're saying you don't want to see that or you don't need to see that, but that's okay. So this is the square root of 1, that is just 1. So this thing right here is a complex number of magnitude 1. Complex number with modulus 1. That means it lives on the unit circle in the complex plane. So there's I, there's 1, there's minus 1, kind of, should be right there, and then there's minus I, kind of right there. This number is just the one you get by sweeping around the unit circle theta radians. So here's theta, and here is cos theta plus I sine theta. That's a very important fact to remember here. We'll be using that a lot. The unit circle in the complex plane is going to play a very special role for us as we start digging into the geometry. So this is actually your direction. It's kind of a direction vector. It tells you where to point, and this tells you the magnitude to scale in that direction or move in that direction. So locate direction, move this far in that direction. And remember that this guy right here is just the modulus of the number. So let's do a little warm up. Now at least some of the problems might make more sense if you haven't had a chance to really dig into this or you've never seen this stuff before. So let's do some practice. Convert from rectangular to polar form. Let's do a little practice. I'll give you a list here. Oh, Ella, what was the problem that you asked me about, the 7?
Oh, it's like 7, 002, 001, and I thought it was 3 separate numbers, but it's just 7 million.
Yes, so yeah, that was really confusing because everything is separated with commas in that list. So in one of your problems, this is the number they want you to convert. to polar form. It's goofy. It's a goofy problem. And it's goofier because it's in a list of things separated by commas. So Ella came and said, "Hey, Ketra, we're looking at this, and are we supposed to know what 001 is? Why is it?" Right. So, good question, Ella. So let me just give you a few to do here. That's boring. That's better. And yeah, I do want to do that. That would be. Can you please convert each of those to polar form to the best of your ability without a calculator? Let's try without the calculator, just to have fun. You might want a calculator for some of those problems because they're weird. But in general, I really don't like them in class. You don't get powerful by using calculators. Lost Nike. Didn't even really need to be back there, I guess. Always helps to draw a picture as well, so I highly recommend sketching out where those numbers sit roughly. Visuals in this class are going to be indispensable, and your ability to visualize is going to need to develop. I'll slowly go through them as we, so just give you time. Prove something about E or something. Here, find this loop. You probably already, we did that in class, you probably already know it.
Yeah, I'm just trying to remember the like.
Oh, good, you have something to remember, good.
Yeah.
I'm like the guy in the high-speed chase, trying to like just throw oil barrels behind me instead. Scale is pretty rough here. How far you'll be able to get on this depends on how much trig or special triangle stuff you remember. Everything here is something you can get exactly, unlike some of the homework. keep in mind these angles can vary by 2 pi, plus or minus 2 pi. So there's actually infinitely many right answers. I'm just picking the shortest route there. This one could also be. There's lots of ors that could follow it. And then this one is, what is this? And I will go through this. I'm not just tossing this stuff up hoping it works for you. That's super shitty scaling. But it is what it is. So that's negative pi over 6. I'll go through how I got those. I just want to kind of get them out there. So if you got them, you can check yourself and get a sanity check. No matter how you do this one, your answer should involve a pi over 4-ish, and this one should involve a pi over 6-ish thing. Everybody, a few more minutes. Erase this stuff and kind of start working over here. Cool. Is it okay if I kind of start working through these? See folks still working. So 7i is right here. I think what angle, so here's the line segment associated with it. From the origin, I draw a line segment to the point. That distance will be r. So r here is just 7 units. And I'm really glad Christian tossed that I into that formula earlier here, just because we want to think of absolute units for that r, right? So I wouldn't involve the I at all. It's just 7 units. Walk 7 in that direction. So r is 7, and the theta would be, remember this is 2 pi all the way around. So pi gets me halfway, pi over 2 gets me 1/4 of the way. So here theta is pi over 2. And then I just plug it into the r cosine theta plus I sine theta form. What are some other thetas that are also viable? That's one out of the infinitely many. Give me one other.
-3 pi.
-3. Yeah, I could have gone this way if I was like being like that. So it could have been -3 pi over 2 as well. Totally kosher. And then add 2 pi, multiples of 2 pi to those, and it's all good. Also 5 pi over 2, right? Do a 2 pi plus a half a pi, totally kosher. So this thing here is just, well, I got the answer right over there, but that's how I got the angles. Just good. All right, cool. So let's do where things start to get funkified. So we've got 3 minus 3i. So pick a 3, that means that's 3 units, that means that's the same 3 units. So that's minus 3i. That's 3 minus 3i. And draw that line, and now use Pythagoras stuff again, right? So this is 3, so this is 3 square root of 2. Yikes. Is that kosher? How I got that? Let me make let's see. So if this is r, remember that r is the square root of the x component squared plus the y component squared. And I guess that's a negative 3 there, so like so. And then you can simplify that down and convince yourself that that is 3 square root of 2. So that's my radius. And then I recognize this as a perfect triangle. It's a multiple of this triangle that is 1, 1, square root of 2. And that's a 45-degree triangle. I would keep that friend at hand, as always. So I recognize that a triangle that has a right triangle that has 2 sides of the same length is this triangle, or a scaled version of it. Pi over 4, pi over 4, 45, 45, 90. Because we're working in the plane, so triangles still work the way they always did for you. So this must be 45 degrees right here. But since I swept this direction, it's a negative pi over 4. Cool. Okie dokie, cool. And then, so then I got this form here, and then I was just being saucy and did it with a positive angle measure. So all the way around would be 2 pi, which is 8 pi over 4. Back off one of those pi's over 4, and you get 7 pi over 4 to get you there. Last one, the other special triangle looks like this. So we've got negative 1. Square root of 3 is like 1.7, so it's a little more than twice that distance. And here's my point. And I recognize that as, I wasn't even trying to be saucy here or anything. I was just trying to say, hey, look, I've got a triangle that has negative square root of 3 on that, and 1 there. And I think about this friend, this really good friend of mine and yours, this 90-degree triangle. And that's pi over 6, that's 30 degrees, 30 degrees, and 60 degrees. Right there. And I literally just have that triangle flipped and rotated to be in that position. So that means this side here, I could either know this or call Pythagoras to give me a 2 here. And then this angle must be pi over, wait, did I screw this up? Did I just, wait. Oh, son of a gun. I don't think that's right. I think I got this ass backwards. So this is actually pi over 3 right here, right? So it's not the pi over 6 that I have over there. I'm glad we're doing this again. So what I actually have is a pi over 3 pocket right here. Here's the pi over 6. It's opposite the shortest side. Smallest angle is opposite the shortest side. Next biggest angle is opposite the next biggest side. And then the biggest side is opposite the biggest angle. That's just the way that all rolls. So this angle here is the one I want, and that is pi minus pi over 3, which is 2 pi over 3. And so that's a negative 2 pi over 3 to get me right to there. Boy, I was getting sloppy. So this is negative 2 pi over 3. Or what's the positive version of this?
4 pi over 3.
4 pi over 3, exactly. So this should be negative 2 pi over 3, or 4 pi over 3, in both of those. Cool, sorry about that. Is this all good? Do we feel ready to finish that homework part? And if not, you've got till Friday. We can talk about it on Wednesday, so please just look at it before class. We'll clear up any problems you might be having. This is really cumbersome, writing out that cosine plus I sine, so we have shorthand. And that's where Euler's identity comes in. So instead of writing out all of this, we will use Euler's identity. And Euler's another one of those just demigods of math. You've got Pythagoras, but Euler did so much. Euler's got a number. What is that number, approximately?
2.71.
Oh, I like it. Yeah, that's lovely. So I always remember it's 2.7, 1828, 1828. And that's really the only date in history I can remember. And I don't think it's a date in history that means anything other than it's in this number. But then that just keeps on going. So that's approximately Euler's number. This is the pi of calculus. So pi shows up with circles, pi shows up with measurements. This is the number that shows up from calculus stuff, right? Just quickly. That's special. It's the only function whose derivative is itself. It's a very, very special number. And it arises naturally from calculus stuff. So Euler's identity says the following, that e to the I theta is equal to, I almost got ahead of myself there, cosine of theta plus I sine of theta. It's literally just a shorthand for this expression that we wrote way too many times. This is what you can see a derivation of in the content area. So do check that out. If you don't remember how to derive this, if you can't sit down and derive this on your own right now, watch that video, very short. Some Khan Academy crap. It's like, I hate using Khan Academy stuff, but it was literally the first thing that showed up and I was being lazy. So we will use this. This is incredible. Notice that that also means that in the complex plane, on the units, where's the undo button? On the unit circle, there's 1, there's I, there's -1, there's -I. E to the I theta is on the unit circle, and it's precisely theta radians from standard position. So e to the I theta lives on the unit circle. So that means our polar form, all this stuff here, this is just e to the pi over 2i. So this number here, 7i, is 7 e to the pi over 2i. And come back and fix all of these. Let's get rid of this guy. So this is 3 square root of 2 e to the negative pi over 4i. And that's just shorthand. It's just shorthand for this piece. Just think of it as compact notation. If you think about it too hard, you might hurt yourself. The only way to think about it properly is with that derivation video. But other than that, think of it as compact notation for this expression. And so then this guy here is 2e to the negative 2 pi over 3i. So let me ask you a few questions. Can you please convert this number to polar form using this exponential notation? So this is what e to the what? Fill in the blanks. So draw the plane out, mark I, and think about it from sweep and distance. And do this one too, please. Those are locations on a unit circle. So glad to be here. You're my mileage may vary on that sensation. You're all good. You're all good. Try keeping an eye on you. Lurking back here like a creeper. That is thick, man. You got it super zoomed in, don't you?
Yeah.
Yeah. What do we have to sweep to get to I? How many radians?
Pi over 2.
Thank you. Otherwise, I'll have to keep just gently stroking the board like this. Yes, pi over 2. Thank you. Pi over 2. So that is the thing that goes here. This is pi over 2 I. I just literally tack an I on. Take the theta, tack an I onto it, make it the exponent on E. That means cosine of pi over 2 plus I sine of pi over 2. What is the modulus of I? 1. Very nice. So I can also be written like that. Things are starting to look weird. Right? It's starting to get funky. If that doesn't look weird to you, I don't know what to do to you to make that look, because that looks weird to me, and I've been doing this stuff for a long time. That looks strange. I'll say more about that in just a second, because I want to show you something stranger. What about -1? How do we get to, what do we have to sweep? Pi, half the revolution, so pi. So I sweep a pi, and I tack on an I. What is the modulus? 1. Remember, the modulus is always a positive number. If you want a negative number, you have to sweep towards that negative direction. So it's just 1 e to the pi I. Any questions on either of these two things? Because I want to do something weird with them really quick. Just like recreationally, right? Something weird. This thing here, if I add 1 to both sides, is called Euler's identity. This is one of the most famous and amazing equations in all of mathematics, linking together the 5 most important constants in all of our world that we know of. There is 0. I tell you, when 0 came around, every time a new number comes around, somebody dies. Somebody's upset about it. Not anymore. We've more or less gotten sensible about things. But when 0 came about, you know, and it was mostly the church back in the day, like forbidden knowledge, talking about nothing just upset people. Talking about negative stuff upset people too. The first 0, I think, and somebody can tell me, history of math people, where's the first 0? Like on a Hindu temple or before that? I'm pretty sure it's in a Hindu temple. We found the first 0 on top of the temple. It was just, really, the Hindus like were so advanced in terms of numbers. They were the first to conceptualize numbers so big they could never be experienced in life. I think, so one of the things about Hinduism is the universe goes in these cycles, and it's created, it's really beautiful, shit starts to disintegrate, things get really crappy, not at all like what's happening in the world now, and then everything dies out, and then it's reborn again. And that whole thing is called a Kali Yuga, and it's just like billions of years along, the Kali Yuga. Oh, you go, help me. Yeah.
So it says Mesopotamia.
Mesopotamia.
Yes.
That
The
figures.
Mayans invented it independently circa 4 AD, but it was found in Mesopotamia in 3 BC. It was later devised in India in the mid-5th century, spread to Cambodia near the end of the 7th century, and into China and the Islamic countries at the end of the 8th.
Wow, beautiful. What didn't the Mesopotamians do? Yeah, it's crazy. The Mesopotamians, did I talk about them and Jupiter in here?
Yeah.
Yeah, okay, yeah. So like like they literally did everything. And then we pretended like we did it again later. So 0, incredible, nothingness. What comes from nothingness? Well, something, the one, the unity of everything. You can't get anywhere from 0 unless you have 1, the unit. Just, unity. E, we talked about that. That's the pi of calculus. Well, this is the pi of just pi. The pi of the pi world. This is pi of circles, pi of just spinning around and moving forward. And then, our good buddy here that we're hanging out with. But they're all related in this beautiful equation. It's insane. Look at this equation. I was trying to keep Lou busy with this question. What is I to the I, which just sounds stupid? Well, we can use this to find out. Because I'm going to take this I and rewrite it in polar form. And I'm going to leave that I up there. What do you do with exponents when you have this composed exponentiation? In other words, what do you do with those exponents? Multiply them, right? So here I'm going to multiply them. What's I squared? I to the I is a real number. It's that real number. Of course, involving E and pi, and there's a 2 in there. And that's my favorite. I kind of like that better than this one, just in terms of like brain-shattering things. Okay, that's enough. That's enough. Let's move forward. Why do we care about polar form? Because it gives us insights. Insights we could not gain otherwise. So for example, let's see some of the insights. So polar form, much like a lot of different forms in math, reveals secrets. Secret mechanics. So for example, let's say I got 2 complex numbers. Z is RE to the I theta, and W is SE to the I phi. So let me sketch them out. Let's rotate by theta. So there's theta. And then move out R units. So that's R units. So this must be Z. Z can be anywhere, I'm just pretending it's there. And then W, W says, so go out phi degrees, so rotate phi degrees, or radians. And then move out S units. And that must be W. Now we know how to multiply these together normally. So if I say Z times W in rectangular form, you got to do the FOIL, group together all the I stuff and the real stuff. You've done some of that, hopefully. But look what happens when I do it in this polar form. It's this number times this number, and then I'm going to regroup. So I'll bring together the moduli. So my new modulus is just the product of the old modulus, old moduli. And then here I'm going to add these 2 angles together, because that's what you do when you multiply. You add your exponents. So the insight that I just gained from simply moving to another form is that when I multiply 2 complex numbers, I multiply their moduli, their lengths, and add their angles. Very nice. So to multiply 2 complex numbers, new modulus equals product of moduli. And the new What is the word for the angle? Did anybody do the reading? What do you call the angle? It's a word that's very nice. Starts with an A. Argument. Yeah, actually, yeah, beautiful. Beautiful. Lovely. And the new argument, which is just, this is just the angle, equals the sum of the arguments. We just see that from that simple computation right there. If I was going to do it with polar forms, I could actually, let's see. Yeah, let's just leave it as this. I think the picture will get pretty atrocious if I do what I was thinking. And then let's see something else that's really cool. What if I have that z? So again, z is still this thing here. If I raise it to a power. So let's just do it. So that's, this to the nth, and distribute that, use the powers rule for this. That's r to the n, e I theta to the n. We just saw that just multiplies that by n. So that's r to the n, e to the I n theta. So to raise a complex number to a power, you just raise the modulus to that, convert it to polar form, raise the modulus to that power, and just multiply the argument by that power. So what do I mean by that? Let me give you an example. Let's say I wanted 1 plus I raised to the 100th power. One way to do this is pretty painful. You like to foil? Foil it. You won't be done by the end of this month, no doubt. Start 1 plus I times 1 plus I. Okay, I got that squared. Now I got to do that times 1 plus I. Painful as can be. 99 foils. Or I convert this to polar form. What is this in polar form? Take a minute. What is 1 plus I in polar form? And use the E form. So it's going to be something e to the something I. What are those somethings? And they're not the same. What's the modulus? Square root of 2. Pythagoras is rolling in joy, wherever the hell he is. What's the angle? Pi over 4. So that perfect triangle again. Yield 45, 45, that's pi over 4. So I convert this into the problem 1, square root of 2, easy buddy, e to the pi over 4i to the 100th. Now it's cake. Got a little more work to do, but here I've got square root of 2, so that's 2 to the 1/2 raised to the 100. That's just 2 to the 50th. That's a big ass number. I don't know what that is. It's a big number. Calculator friends. Does your calculator do 2 to the 5th? Oh, probably. That's probably not too bad, but.
It's 1.12 times 10 to the 15.
That's big. Yeah. That's a rough approximately. Yeah. Big. E to the what? What is the new exponent on the E? 25i. 25 pi. Thank you. No, yeah, I think you said that. I just said it wrong. But I knew what you meant.
I think I said it wrong.
I'll take it. I'll take the L on that one. Where does this land us? Because that's okay, but it's not super satisfying. I would love to go back to rectangular form. What does 25 pi's get me to. So start here. 2, 4, say what? Yeah.
Pi.
Yeah, exactly. Take out multiples of 2 pi, right? Because those don't count. They just land you back. So this is equal to, let's take this up here. So this is 2 to the 50th, e to the, now watch this. This is 2 pi times 50, whoa, no, times 20, times 12. Son of a gun. Let me just write this up. So 25 pi is equal to 2 pi times 12. So that's 12 full revolutions plus just a single pi. That's what I mean to say. So this is equal to 2 to the 50th, e to the, watch this, 2 pi times 12 plus pi I. And so that's 2 to the 50th, e to the, just a nice old spin around 12 times thing. So I'll put it here. I'll put 24 pi. Could have just done that in the first place. That probably would have been good. E to the pi I. What is this thing? What is that number? Do it in your head. Spin 24 pi times around. What do you get?
1.
1. Beautiful. Get you right back to the start. What is e to the pi I? -1. There's our final answer. That's pretty cool. That's incredibly powerful. Or you can foil it. Your choice. All right, one last thing, because I want to get to this little problem that I'd like us to at least work on, maybe between now and then, or whatever. It's not homework. But what about division? Let's start talking about division. So let's actually talk about the rectangular form first. But we gain a great deal of insight based on the polar form. But first, let's do the rectangular version so you can see how to handle this. And I think that the homework assignment that I gave today has just got some division problems in it. So you'll be able to start on that if you want. So if I've got z equals x plus iy, and I've got w equals s plus it. Boy, that doesn't look good. So let's see here. A plus bi, or ib, there we go, I like that better. I'm just like 10 years old in my brain still. Some things never leave. So if I want to take z divided by w, here's what I do. So let's write this up. To do this, you multiply by the conjugate of the denominator. So I multiply by a minus ib on the top and the bottom. So notice this is just w conjugate. So what I've done here is I've taken z over w times w conjugate over w conjugate. You would have to then FOIL this stuff out, but here's the good news. This is actually that homework problem I started off the hour with. This is a number times its conjugate. You're going to show that that is actually just its modulus squared. That's a squared plus b squared. You can check that out pretty easily. And on top, you've got to FOIL this stuff out. I don't want to write it out, it's pretty unattractive. The basic rhythm to remember is just multiply by the conjugate of the denominator. So what you'd get is this. The point of that is the bottom becomes a real number. That's easy. It's just some algebra. You'll get some practice and we'll talk about it undoubtedly. And I've got just like 6-7 minutes left. So let me do the polar form. So let's do that over here. In polar form, again, Z is gonna be R e to the I theta. W is gonna be, what did I use, S? Thank you, S e to the I phi. So Z over W. I'm gonna do something a little different here. I'm not gonna multiply by the conjugate. I'm just gonna write these forms out. What's the new polar form? So what's the modulus? These are gonna mix together, and these are gonna mix together. What's my new not E part? So we're gonna have E to the something over here. What's in front? R over S, Q. Just R over S. So the new modulus is just the quotient of the moduli. What's the new, what do I do with these angles when or what do I do with these exponents? Subtract. So it's gonna be I theta minus I phi, and that's I theta minus phi. So we subtract the angles. So divide moduli. Subtract the arguments. I wanna just leave you with a problem, and I wanna maybe spend a few minutes just thinking about it. This is kind of hard. So we're just gonna start it and then we'll pick up with it on Wednesday. But it'll give you a key insight into the way some things work in this town. So let's take a circle, a unit circle. And here's the diameter. So this is gonna be 1 minus 1. This is I up here. And here's 0 right in the center. So it's the unit circle. I'm going to inscribe a right triangle in this. And I'm going to say there's Z, that's a point on the unit circle. Prove that no matter where Z is, that's a right angle. So now let me give you some help. I'll leave you with that. This is not a homework problem. This is like, if you're feeling it, give it a shot. I'll work it through with everybody here. But here's the fact you're going to need. If I have a complex number Z0, an array that emanates from Z0 through Z1. So array is just a line that extends in one direction. And then I have another ray that extends through Z2. This angle here can be found as follows. So that theta is equal to the argument. It's the difference between this big angle and this angle, or this angle and this angle. So it's going to be the argument of Z1 minus Z0 over, actually let's do it positive. Let's do positive. So Z1 minus Z0 over Z2 minus Z0. This formula will come in handy from time to time. Here's a tip. Make this your Z0. We don't have time to do this today, but it's really cool that you can prove this must be a 90-degree angle. Like, how to do this otherwise, I don't know. That's the kind of shit that scared me when I started on this class. Like, oh my God, I don't know much of anything. But if you do it with that fact, and this picture, and these rays, you can do it. So give it a shot, or not. It's okay either way. Mostly get your homework done. Ah, friends, thank you. Yay. See you on Wednesday. Today's the last day to drop. Just say, I hope I better see everybody here, no eye contact with anybody, show up on Wednesday. I'm sweaty. Yeah?
Can I ask you, now that we learned, I don't even remember what it's called.
Polar form, just call it polar
Polar
form.
and this, it's the dot, so
Oh,
I-
prod, that's just multiplication. Yes,
When
yes.
we learned to do it, maybe I just skipped it in the textbook or something. I
Yeah.
followed these out, but now I'm thinking this is the answer instead, cause you do this,
There must be something.
this, and
Yeah,
you add
I don't know, I
the
don't think we're
And-
very good at picking up those.
yeah, huh, yeah. Good
So I
question.
don't know what it is.
I'm just making him so happy.
Thanks.
I'm embarrassed you.
Oh, that's okay.
I just tell people stuff. I tell people good stuff. I never tell people bad stuff.
They send us
But
an email
Very
for
positive.
They really, yeah, it's very
The
positive.
CD
But like
application.
people don't tell
Oh.
people nice stuff about them, right?
Says not to worry about
No one
that.
ever says.
Yeah, I got the legal
The nice
one already,
things that they
so-
can
Oh, nice.
say.
Yeah.
Is
That's
yours,
true.
yours is on the same day?
People I know around here.
I don't know, we had to schedule them.
Not you
Why
guys.
isn't it not giving me the same answer, I guess?
Yeah, no, I
Yeah.
think that's a
I think they're
brilliant
on, like, the same
question, so
days,
let's take a
'cause
look.
it-
So we've
On
got,
the important dates, it had it over the same time chunk, but I think they have different times set aside for.
so you foiled, so we got
Yeah.
two, and then our outer,
Yeah, cause I'm
Probably
not
doing
doing
some
it till
stupid
like,
mistake with the plus minus, that's all they're gonna
yeah, it's.
Like this morning when I was in the class and I was like, oh.
and then the outer and the inner cancel, right?
Uh-huh, so
Yeah.
there's no eyes.
Cool,
Unless
so
I
we
like
just
live in grad
get
school, so I
8.
can get free housing, but you know.
So, I think that what happened is you didn't square that 3, because it's,
Uh-huh, I did, in fact.
or something like that. Yeah, it did in fact.
Who knows,
Yes,
maybe it's a
ma'am.
lot
So,
better than other
It's
Yeah.
just,
Yeah. Could be.
so when you do
It's like
Z
in
dot
college
U,
especially,
you get
those
R.
classes or something like that.
When,
that is?
so let's do it your other way. So then this guy here was 2e
Yeah.
to the pi over 3i.
All we get is.
And then this one was 2e by, see you later, thanks for
Yeah,
the
but
later.
these are, they're doing CAs now instead of.
Yeah.
But the other one was you?
Do you know how
No,
much
this
they pay
one,
for
this
these?
one is this.
I don't know how much it is, I know this
The
year,
other
I know
one,
this year
you-
they
It was
got
3,000.
Is
year,
for
yeah.
E
For the year?
I
Yeah, you're
five.
right.
It was like 1,500 for the semester,
Oh.
that's what one of them.
So,
One of them.
I'm sorry, what was
they
it?
get the
The
same
one that you're
rate as
dotting,
all the
This
other
one
U
here?
students
is
right now,
four
but she
E
told me that she only
I
got
5 pi
1,500
over
for the semester,
That
so
sounds
get, like,
right.
the worst
Four
of
E
it.
to the I five.
yeah.
Yeah, no, I
Cool.
was showing you
That all
really
looks legit.
my match.
So, you multiply them
Yes.
together, you get 2 times 4.
It's,
Yeah.
Add the arguments,
But I
you
mean,
get
like, no offense, but
2 pi i.
they're not
Yeah,
doing
and that's
it
what
a
I
lot
wrote.
right now.
And,
Is my final
and that
answer.
is beautiful.
No, the first couple.
Is that
were
different than
like
this?
in Borilla.
Yeah, but I mean,
So
like,
when it's 2 pi, so you start at 0, spin around 2 pi, where do you land?
You gotta go.
Where you started.
Exactly.
yeah.
So you're back
No,
on
but I
this
mean,
real
like,
axis,
programming
then you
wise,
move out
programming
one.
wise, it's like-
It is the same.
It is
answer.
exactly the same.
That's
And the only
awesome.
reason it didn't look was because you
That
didn't,
has to be
you left this like this as
Yeah.
opposed to that.
But
Okay.
also, I think.
Okay, that makes sense. Cause I was like, well,
But
they
I know that
should
they
be the
have,
same
like,
thing.
diminished
You're right.
responsibilities as
okay,
right now. I think that
cool.
they also don't
I
have to do
will-
goals anymore.
I think I need to redo this whole page, cause after this class, this
Besides
class,
the front.
this is
Well,
the
well,
front.
Nolan,
These are fine.
Nolan made them.
This
do
one
digital.
can-
Oh, okay.
I have questions for
But I also
these, so
think
for
next year they-
all of the interesting points they give us, I just
Yeah,
used the
that's
art
fine.
plan.
That's
Okay.
it.
And it,
Yeah.
no, about.
And then I did the,
Oh, good.
these ones
This
things
one
because.
is-
Apparently it was only.
Oh, so Ella and I were talking about this, so a couple of these arguments are off.
Okay, cool, that's what I just figured.
So let's take a look. So, I think because you're adding the pies and 2 pies incorrectly,
You gotta go.
at the wrong, you should be.
I wasn't sure, the example that I was giving Alex, can I still
Yeah,
use
yeah.
it? Was that in the book, it just had like, well, it goes all the way here, and it had an angle here.
Oh, hold on, I'm gonna shut
Oh,
down
no, no,
the,
no.
Cal, thing.